Okay, now let's discuss heuristics for our 8 puzzle problem. First of all, what is a heuristic? Heuristic basically is only is only an informed guess. It's an informed guess of the next step to be taken. Okay, so heuristic is only informed guess, and that enable us to choose the next step that could be taken in solving a problem. Okay, good. Now let's look at this situation. Our problem is that we have a start state, and we need to move in a way from one state to another state that we reach eventually to this goal configuration of tiles. Okay, but the question is, how would we choose? How do we go from this state to which of these three states? Which one would be better? Okay, and for that, we could define the rules, okay, or our guesses, uh, based on some criteria. Now, what we could do, we could use this sort of criteria, simple heuristics, where actually we count. Uh, Let me just get back the pen. Right. Which basically we count the tiles out of place in each state. For instance, if this is my goal state, 1, 2, 3, 4, 5, 6, 7, and 8, this sort of configuration. If I look at this particular state here, um, how many tiles are out of place? So comparing with the goal state, 1, 2 is out of place, 2, 6 is out of place, 3, uh, and 7 is out of place, 4, and 1 is out of place, 5. So we got 5 tiles which are out of place. And in this case, we have 4 tiles out of place, which are 2, 8, and 1. Okay. 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 Actually, 3 tiles are out of place, not 4, because it's this tile 2, 8, and 1, and 3, 4, 5, 6, and 7 tiles are in place. So for us, the better this is the better choice um, for our next state to go on to. And our assumption is that the state that has the fewest tiles out of place is probably closer to the desired goal, and it would be best to examine this next. One of the problem with this sort of approach is when we have to consider tile reversal, because just by counting the number of tiles um, which are out of place would not probably give us the best guess or best heuristic. So in this sort of situation where these two tiles have, let me just get back, okay, where these two tiles have to swap. But although visually one is one place away from its desired location and two is one place away from desired location, but we know that if two wants to move from here to here, one needs to get out of the way first of all, and then two would come there, and then one has to one uh, move up there and up there, so it is two places away from its desired goal, from its desired location. Okay. So in this case, we need to use a better heuristic that will take this into account to give us a better fit. So what we could do, we could use a heuristic that is based on sum of all the distances. So what it is, basically we will sum all the distances by which tiles are out of place. One for each square a tile must be moved to reach its position in the goal. For instance, in this case, if you look here, we need to move to one place to its desired location here. So we will have one, that 2 needs to move 1, and 8 in this case needs to move 1 and 2 places. So we'll put 2 for 8, and then 3, 4, 5 doesn't need to move. Then 6 needs to move one place uh, there, and then 7 also needs to move one place down there, and that is 1 again. So the sum of all the distances by which tiles are out of place, or they need to move, is 5 in this case. Oh, I beg your pardon, because we didn't take into account the movement of 1, so that is going to be another 1, so that is not why it's 6. Okay, and right, I think that's correct. So the sum of distances of out of place for this heuristics are 6 in this case. Okay, and you could compare that with tiles out of place, and it's giving you a better fit. Okay, now we have seen a simple heuristic, um, a sum of all the distances. Okay, out of place, and this heuristic is we take into account the number of tiles which needs reversal, direct reversal, and we multiply with some small number, in this case with 2. But you could see there is no difference between from all these three states if you use this heuristic. Okay, although we want to take into account if there is a direct reversal is involved. So the better solution would be if you could use a heuristic which add these two together, and if there is, for instance, a tile which need direct reversal, it will have a value here, and that combine these two would give us a better uh, heuristic or our guess. Okay, and this could be our fourth heuristic, which could be a better choice. Okay, another important concept that we need to understand in um, understand the concept of heuristic algorithms is the evaluation function. It is basically the criteria to which we we will test our condition against, and then we will make a move in deciding which direction we need to go on for searching our goal state. Now it is evaluation function f is a sum of two components. So whichever state we are on, n signifies any state, whether it's first or second or third or 28 or whichever. Right, it has two components, Gn and Hn. What Gn in our case, it could be it measures the actual length of the path from any state n to the start state. Okay, we could think of this for our case, it could be the distance from the starting state. So if we have a start state and we have uh, descendant states, for instance, and let's say we have another states there. So the distance from the starting states to its descendants. So here the distance would be 0. Here distance from start state to its descendants, which is this level, is 1, and further down it is from its start state to its descendants is 2, and so on. Um, 3, and so on. Okay, so it it could we could measure the, the distance from start state to its descendants by maintaining a depth count. So each we would, using this depth count, we could measure how far we are from our start state. Um, and as you can see, the count is 0 at the beginning and is incremented by 1 for each level of the search. So this signifies, in our case, g of n, which is the actual length of the path from any state n to the start state. So we could, whichever state we are in, so we could say what is the length of our path. In this case, if we are here at this point, so the length of our path would be 3. So we could measure it directly. The next bit that we need to understand is what is Hn, which is basically is our heuristic estimate. I mean, what is our best guess? And if you from our previous slide, we could use our best guess based on simple heuristic or some of tiles out of place, and some combination of um, uh, tile reversals plus the sum of uh, tiles out of place. So for each tile, we would assign a value of hn. For example, for if if this tile is at okay if this tile is at some location in our tree, for instance, if this is here, we will assign hn value that would be um, uh, if you're taking these if you're taking our heuristics as sum of these two. Okay, let me just figure out my pen. Okay, so that would be 6 in this case, and so the if this is 0, 1, and level 2, so the f of this tile, let's say the tile name is w, f of w would be uh, g of n, which is 2 in our case, g of w, plus uh, h of w, in this case that is 6, so the it is going to give us the value 8. Okay, and this is going to be our evaluation function value. Okay, I hope this is clear now, and moving on to here. So this is again this is signifying the same concept, which um, basically look at the level, and each level uh, the value of g of n, uh, the actual length of the path from any state n to the start state, and h of n. So we will assign each state. In this case, we're assigning each state a value for its heuristic estimate. In this case, is 6 and 4 and 6, and we could calculate the function f of n, and that gives us the criteria. So we could use this to choose a tile. So have a guess which tile out of these 3 we should choose as next option. This one, or this one? I suppose you already have guessed it will be this one, but that gives us the lowest cost. Okay, right, so we now understand what are the heuristics and how these are used in the algorithm, heuristic based algorithm. So I'm going to use an example for a and a star algorithm, and we'll dry run the algorithm to see how it's used in the actual algorithm. Okay.